All right, hello there, 2D folks. Wish I was there. Whoever's there supervising you, if they could please just pause the video, give you a chance to write down the 3-minute review question and give it a go. And then I'll explain it in just a few minutes. So pause the video now. Okay. So I hope you've had a chance to try the question. The idea of showing that that point is a solution to a system of equations means that this point has to be on both of those lines. And if this point is on both of those lines, then it is a solution. So I've got it sort of set up here, and we're going to check it out. So for line 1, is it on line 1? Well, the idea is it's got to satisfy both the left side and the right side. The left side is just y, the right side is 15x minus 78, and the y is negative 18. So hopefully when we work out this right side that it ends up being negative 18. So we got 15 times 4 minus 78, clunk that into a calculator, and you get minus 18. And that works out. Now notice that doesn't say that it's a solution to the system. That means that it's on that line. And so we can say, so for negative 18 is on line 1. For line 2, similar calculation, except for the right side's pretty boring. The right side is 0. So this hopefully will work out to 0. And I think it does. Jam that into a calculator. Bam, 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 bam. Calculator, calculator, calculator equals 0. So that works out, and we can say so that is on L2. So I put those two facts together. It's on L1 and L2, and then those two things together tells me that it's a solution. Therefore, for negative 18 is a solution. Solution to the system. Now, one thing, it's kind of weird not having me there, I realize, but if there's ever a spot that you're not sure of, jot your question down in the margin, right? And then you can talk about that with classmates after the video's over. And this video, it's up on YouTube. You'll be able to access it later and watch it again if you like. It's kind of one of the advantages of not having me there, even though there's lots of other ones, like me not hassling you about stuff. But I'm hopefully whoever's there is hassling you about something, so just to take my place. All right, so the lesson, and I think you'll have a handout for this. The lesson is called Weird Systems of Equations, and something must be about these that makes them weird. And so write down the date, and hopefully there's enough room for you there. Again, I've sort of set up my set of axes, and I'm going to try and go pretty quickly through this, folks, so try and keep up. And I'm going to talk about line 1 and line 2. Maybe I'll get a different color here. This is line 1. Maybe I'll just call that 1 like that, and this 2. So for line 1, it's already in slope y-intercept form. So I'm going to start at the y-intercept of negative 4 and then go up to right 3. So at minus 4, start, and then I go up to right 3. I'm off the graph, so I'm going the other way. Down to left 3. Down to left 3, and I've made an error already, haven't I? Did you notice that? You see what error I made? I didn't start at minus 4. So it's just like I was there, making mistakes all over the place. Serves you right if you're just copying it down, by the way. Minus 4, then up to right 3, up to right 3, down to left 3 is the same thing, and then we'll draw the line. Nothing particularly weird about that one. Looks fine and dandy. But maybe something weird happens with the second one. I'm going to change the color of this so it's blue. There, beautiful. The second one is blue. 5x minus 3y equals 15. This feels like it's an xy intercept one, right? Whenever we see that the points sort of match up like this, I'm going to do x and y intercepts, right? So when x is 0, then I'm left with only this part. So for instance, that if that's gone because it's 0, then what's y got to be? Divide by negative 3, that's negative 5. And then when y is 0, this part's gone, and x is 5 times x equals 15, divide by 5, x equals 3. And so then I can draw this graph. 0 minus 5 is way down here. 3 zeros right here, and then I can draw the line. Now what's particularly strange about this one? Well, not much of anything really, except for perhaps that the crossing point's in the middle of the square, and I can't really see what the solution is. So that's kind of strange. You know, the solution is right there, right? One solution, but you know, we don't know what it is. It's just a guess. It looks like it's about maybe 0.8 and negative 3.5 or something like that. But that's not very accurate, right? This is a guess, and maybe that's what's weird about this system. The other ones we'll see are even weirder. Okay, so for instance, this one, 3x minus 3y, I'm going to call that green 1, and this is green 2. That sounds like a xy intercept one as well because it's in that form, 0 and 0. So when x is 0, y is minus 4. Then when y is 0, x is negative positive 4. Right? Let's draw those 2 points. No problem. 0 and negative 4 is there. And 4, 0 is over here. Everything's awesome. Nothing weird. And that line, I should have been labeling these lines, but I'm trying to go quickly for you folks so you can get the homework. This is 3x minus 3y equals 12. And then for the second one, it's in y equals mx plus b form, so that should be easy. This was for line 1. Line 2, the y-intercept is minus 4, and the slope is just 1, right? 1, and we'll write that as 1 over 1, up 1, right 1. And notice this is weird. You know, we're starting at the same spot, going up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. It's the same line, right? It's right on top of each other. Weird. See, I told you it was weird. Weird. Solve these weird systems. Well, what's the solution to this system? All the points are solutions. There's an infinite number of solutions. All points on the lines. Infinite solutions. It's taking a while for my pen to catch up to me here. Good. Infinite number. Little pen, wake up. There you go. Number of solutions. Okay, so that one was weird, right? Solutions. That one's weird. Weird, weird, weird. So this one doesn't look very weird, but let's see. Change the color. All right, let's keep the colors rolling. Hang on. All right, back at it. There is equation 1 and equation 2. For equation 1, we'll do a x and y intercepts. because it looks like that, right? When x is 0, y is 3. When y is 0, x is 6. And we'll plot those points. 2, 6 there, 3, 0 there. 2 points is all we need. Nice. And this one is in the nicer form, even nicer. The y-intercept is -1, and the slope, the slope m is -1/2. And again, we write the negative in up with the 1, so we know which direction to go, down 1, right 2. So y-intercept is 1, down 1, right 2, down 1, right 2, down 1, right 2. And what's weird about this? Well, when I draw that line, where's the intersection point? They never intersect, right? These are parallel lines. And so that's pretty weird. No intersection. Not running out of room. No intersection, which means there's no solution. And in fact, we can say line 1 is parallel to line 2. So that's why there's no solution. So soon we'll be talking about sort of getting a feeling for when these things will happen before we have to plot them. But for today, this is what we're doing. We're looking for, sometimes we have one crossing point, sometimes they're right on top of each other and we have the same line, and sometimes they're parallel lines like this. Now, the question for you, well, there's a bunch of questions for you right there, the homework. The question for you is, how might we figure this out before we start graphing all this stuff? How might we figure this out, whether there's going to be one solution, an infinite number of solutions like the one in green, or no solutions like the one in red, without doing the work? And that, my friends, is tomorrow's lesson. There's the homework. Add that to your homework log and get at it.